Apache Kafka documentation chapter 4. So while we didn't go to chapter 3, it deals with configuration. I skimmed through it and I don't think it's going to be useful for us, not at this point, because it's just going through many low-level configurations and we don't have the full context yet. So we first need to get the whole picture, the whole context, and then go over low-level configuration. Right now, it won't be that helpful. So with that, let's move on to chapter 4, which is the design. So Apache Kafka, documentation, official configuration, the design. Motivation. We designed Kafka to be able to act as a unified platform for handling all the real-time data feeds a large company might have. To do this, we have to think through a fairly broad set of use cases. It would have to have high throughput to support high volume event streams such as real-time log aggregation. It would need to deal gracefully with large data backlogs to be able to support periodic data loads from offline systems. It also meant the system would have to handle low latency delivery to handle more traditional messaging use cases. We wanted to support partitioned, distributed, real-time processing of these feeds to create new derived feeds. This motivated our partitioning and consumer model. Finally, in cases where the system is fed into other data systems for serving, we knew the system would have to be able to guarantee fault tolerance in the presence of machine failures. Supporting these use cases led us to design with a number of unique elements more akin to database log than a traditional messaging system. We will outline some elements of the design in the following section. Persistence. Don't fear the file system. Kafka relies heavily on the file system for storing and caching messages. The general perception that disks are slow, which makes people skeptical that persistent structure can offer competitive performance. In fact, disks are both much slower and much faster than people expect, depending on how they are used. And the properly designed disk structure can often be as fast as a network. The key fact about disk performance is that throughput of hard drives have been diverging from latency of disk SIC. So there is no anymore a need for a disk SIC for the last decade. As a result, the performance of linear writes on JBOD configuration with 7200 RPM SATA RAID 5 array is about 600 megabytes per second. But the performance of random writes is only about 1 kilobyte per second. So we see here a drastic 1000x scale difference, 6000 if we take this constant of 6, scale in the difference in between random seq write and a log serialized write. This is a huge difference. This means that if we can utilize disk for serial writes, we have good performance here. These linear reads and writes are the most predictable for all usage patterns and are heavily optimized by the operation system. A modern operation system provides read-ahead and write-behind techniques that prefetch data in large block multiples and group smaller logical writes into large physical writes. A further discussions of this issue can be found in this ACMQ article. They actually found that sequential disk access can in some cases be faster than random memory access. To compensate for this performance divergence, modern operation systems have become increasingly aggressive in their use of main memory for disk caching. A modern OS will happily divert all free memory to disk caching with little performance penalty when the memory is reclaimed. All disk reads and writes will go to this unified cache. This feature cannot easily be turned off without using direct I/O. I saw this coming from multiple places. The need to turn off the buffering of the writes, which goes first to memory and only then to disk. So even if a process maintains an in-process cache of the data will likely be duplicated in OS page cache, effectively storing everything twice. Furthermore, we are building on top of the JVM, and anyone who has spent any time with Java memory usage knows two things. The memory overhead of objects is very high, often doubling the size of the data stored or worse. 2. Java garbage collections becomes increasingly fiddly and slow as the in-heap data increases. As a result of all these factors, using the file system and relying on page cache is superior to maintaining an in-memory cache or other structures. We at least double the available cache by having atomic access to all free memory, and likely double again by storing a compact byte structure rather than individual object. Doing so will result in a cache of up to 28-30 GB on a 32 GB machine without GC penalties. Furthermore, this cache will stay warm even if the service is restarted, whereas in an in-process cache, we need to rebuild in-memory, which for a 10 GB cache may take 10 minutes. I hope they would elaborate on this. Basically, they store things off-heap on memory, but let's see if there is any elaboration of this. On the something called page cache, we can delve into what is a page cache in later episodes, or else it will need to start with a completely cold cache, which likely means terrible initial performance. This also greatly simplifies the code as all logic for maintaining coherency between the cache and file system is now in the OS. The page cache of the OS is something that basically the cache of the OS for slower storages like hard disks. So we keep the recently used hard disk information on the page cache so it can be accessed more frequently, and it can be tuned. The eviction policies, the cache size, so they tuned it based on their needs. So furthermore, this cache will stay warm even if the service is restarted, whereas the in-process cache will need to be rebuilt in memory, which for a 10 GB cache might take 10 minutes. Or else it will need to start with a completely cold cache, which likely means terrible initial performance. This also greatly simplifies the code, as all logic for maintaining coherency between the cache and file system is now in the OS. The OS is handling all this because we use the OS cache. How exactly? Let's hope they describe. Or it's fully transparent. We don't do anything, we just store to disk and read from disk. Could be that this is the case, which tends to do so more efficiently and more correctly than, but probably I think that they would need to tune what's the size of the page cache, what is the eviction policy, etc. Which tends to do so more. This is also why we didn't go through the configuration section, because it's possible that in the configuration section we somehow tune these parameters, so we need to understand first why these parameters exist, which we see now in the design. If your disk usage favors linear reads, then read ahead, is effectively pre-populating the cache with useful data on each disk read. This suggests that a design which is very simple, rather than maintaining as much as possible in memory and flush it all to the file system in a panic when you run out of space, we invert it. All data is immediately written to a persistent log on the file system without necessarily flushing to disk. In effect, this just means that this is transferred into the kernel's page cache. So everything is written to, we just write, and we trust the kernel to use the page cache. We might tune it. This style of page cache design is described in an article on the design of Varnish here, along with a healthy dose of arrogance. We might read this in a future episode. Constant time suffixes. The persistent data structure used in messaging systems are often a per consumer queue with an associated B tree or other general purpose random access data structures to maintain metadata about messages. B trees are the most versatile data structure available and make it possible to support a wide variety of transactional and non-transactional semantics in the messaging system. They do come with a fairly high cost, though B trees operations are O of log n, normally O of log n, is considered essentially equivalent to a constant time, but this is not true for disk operations. Disk 6 come at a 10 millisecond a pop, and each disk can do only 1/6. So B tree is a data structure, so it's a tree data structure, and we need to seek in this data structure because not necessarily everything is one next to another. So we'll need 6. And each disk can do only one seek at a time, so parallelism is limited. Hence, even a handful of disk 6 lead to a very high overhead. So B trees are good when they are all in memory. But now, we are not all in memory. We said we want to utilize disks, so B tree won't be good for us. Since storage systems mix very fast cached operations with very slow physical disk operation, the observed performance of tree structure is often superlinear as data increases with fixed cache, i.e. doubling your data makes things much worse than twice slow. Intuitively, a persistent queue would be built on a simple reads and appends to files, as is commonly the case with logging solutions. This structure has the advantage that all operations are of one, and reads do not block writes or each other. This has obvious performance advantages since the performance is completely decoupled from the data size. One server can now take full advantage of a number of cheap, low rotational speed 1 terabyte SATA drives. Though they have poor seek performance, these drives have acceptable performance for large reads and writes and come at 1/3 of the price of and 3x the capacity. So they favor Q to B trees, complex data structures. Having access to virtually unlimited disk space without any performance penalty means that we can provide some features not usually found on messaging system. For example, in Kafka, instead of attempting to delete messages as soon as they are consumed, we can retain messages for a relatively long period, say a week. This leads to a great deal of flexibility for consumers, as we'll describe. Efficiency. We have put a significant effort into efficiency. One of our primary use cases is handling web activity data, which is very high volume. Each page view may generate dozens of writes. Furthermore, we assume each message published is read by at least one consumer, often many. Hence, we strive to make consumption as cheap as possible. We have also found from experience building and running a number of similar systems that efficiency is a key to effective multi-tenant operations. If the downstream infrastructure service can easily become bottleneck due to a small bump in usage by the application, such small changes will often create problems. By being very fast, we help ensure that the application will tip over under load before the infrastructure. This is particularly important when trying to run a centralized service that supports dozens or hundreds of applications on centralized cluster, as changes in usage patterns are near daily occurrence. We discussed disk efficiency in the previous sections. Once poor disk access patterns have been eliminated, there are two common causes of inefficiency in this type of system: too many small I/O operations and excessive byte comping. The small I/O operation problem happens both when the client and the server and in the server's own persistent operations. To avoid this, our protocol is built around message set abstraction that naturally groups messages together. This allows network requests to group messages together and amortize the overhead of the network round trip rather than sending a single message at a time. The server, in turn, appends chunks of messages to its log in one go, and the consumer fetches larger linear chunks at a time. This simple optimization produces orders of magnitude speedup. Batching leads to a larger network packet, larger sequential disk operations, contiguous memory blocks, and so on, all of which allow Kafka to turn a bursty stream of random messages writes into linear writes that flow to the consumers. The other inefficiency is in byte copying. At low message rates, this is not an issue, but under load, the impact is significant. To avoid this, we employ a standardized binary message format that is shared by the producer, the broker, and the consumer, so data chunks can be transferred without modification between them. The message log maintained by the broker is itself just a directory of files, each populated by a sequence of message sets that have been written to disk in the same format used by the producer and consumer. Maintaining this common format allows optimization of the most important operation, network transfer of persistent log chunks. Modern Unix operation systems offer a highly optimized code path for transferring data out of page cache to a socket. In Linux, this is done with the send file system call. To understand the impact of send file, it is important to understand the common data path for transfer of data from file to socket. The operation system reads the data from the disk into page cache in kernel space. The application reads the data from kernel space into user space buffer. The application writes the data back to kernel space into a socket buffer. The operation system copies the data from the socket buffer to the NIC buffer where it is sent over the network. This is clearly inefficient. There are 4 copies and 2 system calls. Using a send file, this recopying is avoided by allowing the OS to send the data from page cache to the network directly. So in this optimized pipe, only the final copying to the NIC buffer is needed. We expect a common use case to be multiple consumers on topic. Using the zero copy optimization above, data is copied into page cache exactly once and reused on each consumption instead of being stored in memory and copied out to the user space every time it is read. This allows messages to be consumed at a rate that approaches the limit of the network connection. This combination of page cache and send file means that on a Kafka cluster where the consumers are mostly caught up, you will see no read activity on the disk whatsoever, as they will be serving data entirely from cache. TLS SSL libraries operate on the user space in kernel. SSL send file is currently not supported by Kafka. Due to this restriction, send file is not used when SSL is enabled. For enabling SSL configuration, refer to security protocol. These are configuration on the property files, security interbroker protocol. For more background on the send file and zero copy support in Java, see this article. End-to-end batch compression. In some cases, the bottleneck is actually not CPU or disk, but network bandwidth. This is particularly true for a data pipeline that needs to send messages between data centers over a wide area network. Of course, the user can always compress its messages one at a time without any support needed from Kafka, but this can lead to a very poor compression ratios, as much of the redundancy is due to repetition between messages of the same type, example, field name in JSON or user agent in weblogs or common string values. Efficient compression requires compressing multiple messages together rather than compressing each message individually. Kafka supports this with an efficient batching format. A batch of messages can be clumped together, compressed, and sent to the server in this form. This batch of messages will be written in compressed form and will remain compressed. So we are looking here at optimization on the Kafka level, where it is able to take control of the compression and compress multiple messages together and thus achieve better compression because of repeated headers, etc. Kafka supports gzip, snappy, AZ4 as standard protocols. More details on compression can be found here. The producer, load balancing. The producer sends data directly to the broker that is the leader for the partition without any intervening routing tier. To help the producer do this, all Kafka nodes can answer a request for metadata about which servers are alive and where the leaders of the partitions of a topic are at any given time to allow the producer to appropriately direct its request. The client controls which partition it publishes messages to. This can be done at random, implementing a kind of random load balancing, or it can be done by some semantic partitioning function. So the question is here, do we send a message directly to the Kafka producer, to the broker? Yes. To the broker, yes. We send it directly to the broker, directly to the leader. How do we know who is the broker? All nodes have this information. To which partition exactly do we send it? Because we said it's partitioned by the key and we have multiple. It's done automatically also. Or it can be done by some semantic partitioning function. We expose the interface for semantic partitioning by allowing the users to specify a key to partition by and using this approach to hash a partition. So if we remember, in each Kafka message we had 3 fields: the key, the value, the actual data, and the timestamp. So one of them is the key when we partition by it. There is also an option to override the partition function if need be. For example, if the key chosen was a user ID, then all data for a given user will be sent to the same partition. This in turn will allow consumers to make locality assumptions about their consumption. This style of partitioning is explicitly designed to allow locality sensitive processing and consumers. Asynchronous send. Batching is one of the big drivers of efficiency, and to enable batching, the Kafka producer will attempt to accumulate data in memory and to send out larger batches in a single request. This batching can be configured to accumulate no more than a fixed number of messages and to wait no longer than a fixed latency bound, say 64K or 10 milliseconds. This allows the accumulation of more bytes to send and few larger I/O operations on the servers. The buffering is configurable and gives a mechanism to trade off a small amount of additional latency for better throughput. Details on configuration of the API in the documentation. 4.5. The consumer. The Kafka consumer works by issuing fetch requests to the brokers leading the partition it wants to consume. The consumer specifies its offsets in the log with each request and receives back a chunk of log beginning from that position. The consumer thus has significant control over this position and can rewind it to reconsume data if need be. Push versus pull. An initial question we considered is whether consumers should pull data from brokers or brokers should push data to the consumer. In this respect, Kafka follows a more traditional design, shared by most messaging systems, where data is pushed to the broker from the producer and pulled. So the producer is pushing the data, makes sense, simple, and pulled from the broker by the consumer. Some logging-centric systems such as Scribe and Flume follow a very different push-based path where data is pushed downstream. There are pros and cons to both approaches. However, a push-based system has difficulty dealing with diverse consumers as broker controls the rate. The sender controls the rate at which data is transferred. The goal is generally for the consumer to be able to consume at the maximum possible rate. Unfortunately, in a push system, this means the consumer tends to be overwhelmed when its rate of consumption. Yes, so when we push data to the consumer, we push data to the student who push information, the student does not have control over the amount of data. If the student says, okay, I will now study this, I will now get this, then it has better control of it, falls below the rate of production. Denial of service attack, in a sense, a pool-based system has the nicer property that the consumer simply falls behind and catches up when it can. This can be mitigated with some kind of backup protocol by which the consumer can indicate it is overwhelmed. But getting the rate of transfer to fully utilize, but never overutilize, the consumer is trickier than it seems. Previous attempts at building system in this function led us to go with a more traditional pool model. Another advantage of pool-based systems is that it lends itself to aggressive batching of data sent to the consumer. A push-based system must choose to either send a request immediately or accumulate more data and then send it later without knowledge of whether the downstream consumer will be able to immediately process it. If tuned for low latency, this will result in sending a single message at a time only for the transfer to end up being buffered away, which is wasteful. A pool-based design fixes this, as the consumer always pulls all available message after its current position in the log or up to some configurable max size. So one gets optimal batching without introducing unnecessary latency. The deficiency of native pool-based system is that the drawback is that if the broker has no data, the consumer may end up polling in a tight loop, effectively busy waiting for, do I have new data? Do I have new data? Busy waiting for data to arrive. To avoid this, we have parameters in our pull request that allow the consumer request to block in a long poll. Long poll is like an HTTP request, stays open until there is data, waiting until data arrives. And optionally, waiting until a given number of bytes is available to ensure large transfer size. You could imagine other possible designs which would be only pull end-to-end. The producer would locally write to a local log, and brokers would pull from that with consumer pulling from them. Similar type of store and forward producer is often proposed. This is intriguing, but we felt not very suitable for our target use cases, which have thousands of producers. Our experience running persistent data system at scale led us to feel that involving thousands of disks in the system across many applications would not actually make things more reliable and would be a nightmare to operate. And in practice, we have found that we can run a pipeline with strong SLAs at large scale without a need for producer persistence. Consumer position. Keeping track of what has been consumed is surprisingly one of the key performance points of messaging system. Most messaging systems keep metadata about what messages have been consumed on the broker. That is, as a message is handed out to the consumer, the broker either records that fact locally, immediately, or it may wait for acknowledgement from the consumer. This is a fairly intuitive choice. And indeed, for a single machine server, it is not clear where else this state could go. Since the data structure used for storage in many messaging systems scale poorly, this is also a pragmatic choice. Since the broker knows what is consumed, it can immediately delete it, keeping the data size small. What is perhaps not obvious is that getting the broker and consumer to come into agreement about what has been consumed is not a trivial problem. If the broker records a message as consumed immediately every time it's handed out over the network, Then if the consumer fails to process the message, say because it crashed the request times or whatever, that message will be lost. To solve this problem, many messaging systems add an acknowledgement feature, which means that messages are only marked as sent, not consumed, when they are sent. The broker waits for a specific acknowledgement from the consumer to record the messages consumed. This strategy, the acknowledgement, fixes the problem of losing messages but creates new problems. First of all, if the consumer processes the message but fails before it can send the acknowledgement, then the message will be consumed twice. The second problem is that around performance. Now the broker must keep multiple states about every single message. First to lock it, as it is not giving out a second time, and then mark it as permanently consumed so that it can be removed. Three key problems must be dealt with, like what to do with messages that are sent but never acknowledged. Kafka handles this differently. Our topic is divided into a set of totally ordered partitions, each of which is consumed by exactly one consumer within each subscribing consumer group at any given time. This means that the position of a consumer in each partition is just a single integer, the position of the consumer, the offset of the next message to consume. This makes the state about what has been consumed very small, just one number for each partition. This state can be periodically checkpointed. This makes the equivalent of message acknowledgements very cheap. There is a side benefit of this decision. A consumer can deliberately rewind back to an old offset and reconsume data. This violates the common contract of a queue, but turns out to be an essential feature for many consumers. For example, if the consumer code has a bug and is discovered after some messages are consumed, the consumer can reconsume these messages once the bug is fixed. Offline data load. Scalable persistence allows for the possibility of consumers that are periodically consumed, such as batch data loads that periodically bulk load data into an offline system such as Hadoop or relational data warehouses. In the case of Hadoop, we parallelize the data load by splitting the load over individual map tasks, one for each node topic partition combination, allowing full parallelism in the loading. Hadoop provides the task management, and tasks which fail can restart without danger of duplicated data. They simply restart from the original position. Static membership. Static membership aims to improve the availability of stream applications, consumer groups, and other applications built on top of the group rebalance protocol. The rebalance protocol relies on the group coordinator to allocate entity IDs to group members. These generated IDs are ephemeral and will change when members restart and rejoin. For consumer-based apps, this dynamic membership can cause a large percentage of tasks reassigned to different instances during administrative operations such as code deploys, configuration updates, and periodic restarts. For large state applications, shuffled tasks need a long time to recover their local states before processing and cause applications to be partially or entirely unavailable. Motivated by this observation, Kafka Group Management Protocol allows group members to provide persistent entity IDs. Group membership remains unchanged based on this ID. Thus, no rebalance is triggered. If you want to use static membership, upgrade both broker cluster to some version and use this version and then set a group instance ID. (4.6) Message delivery semantics. Now that we understand a little about how producers and consumers work, let's discuss the semantic guarantees Kafka provides between producer and consumer. Clearly, there are multiple possible message delivery guarantees, at most once. Messages may be lost, but they are never redelivered at least once. Messages are never lost, but may be redelivered exactly once. This is what people actually want. Each message is delivered once and only once. It's worth noting that this breaks down into two problems: the durability guarantees for publishing a message and the guarantees when consuming a message. Many systems claim to provide exactly once delivery semantics, but this is important to read the fine print. Most of these claims are misleading. They don't translate to the case where consumers or producers can fail, cases where there are multiple consumer processes, or cases where data written to this can be lost. Kafka semantics are straightforward. When publishing a message, we have the notion of message being committed to the log. Once a published message is committed, it will not be lost as long as one broker that replicates the partition to which this message was written remains alive. The definition of committed messages, alive partitions, as well as the description of which types of failures we attempt to handle will be described in more detail in the next section. For now, let's assume perfect lossless broker and try to understand the guarantees to the producer and consumer. If a producer attempts to publish a message and experiences a network error, it cannot be sure if this error happened before or after the message was committed. This is similar to the semantic of inserting into a database table with an auto-generated key. Prior to version 0.11, if a producer failed to receive a response indicating that message was committed, it had little choice but to resend the message. This provided at least once delivery semantics, since the message may be written to the log again during resending if the original request had in fact succeeded. Since this version, the Kafka producer also supports an idempotent delivery option, which guarantees that resending will not result in a duplicate because it's idempotent. To achieve this, the broker assigns each producer an ID and deduplicates messages using sequence number that are sent by the producer along with every message. Beginning with version 0.11, the producer supports the ability to send messages to multiple topics partitions using the transaction-like semantics, i.e. either all messages are successfully written or none of them. The main use case for this is exactly once processing between Kafka topics. Not all use cases require such strong guarantees. For users which are latency sensitive, we allow the producer to specify the durability level it desires. If the producer specifies that it wants to wait on the message being committed, this can take on the order of 10 milliseconds. However, so the producer can just wait. However, the producer can also specify that it wants to perform the send completely asynchronously, or that it wants to wait only until the leader, but not necessarily the followers, have the message. Now let's describe the semantics from the point of view of the consumer. All replicas have the exact same log with the same offsets. The consumer controls its position in the log. If the consumer never crashes, it could just store this position in memory, but if the consumer fails, and we want this topic partition to be taken over by another process, the new process will need to choose an appropriate position from which to start processing. Let's say the consumer reads some message. It has several options for processing the messages and updating its position. It can read the messages, save its position in the log, and finally process the messages. In this case, there is a possibility that the consumer process crashes after saving its position, but before saving the output of the message processing. In this case, the process that took over the processing would start at the saved position, even though a few messages prior to this position had not been processed. This corresponds to at most one semantics, as in the case of consumer failure, messages may not be processed. 2. It can read the messages, process the messages, and finally save its position. So first do the operation, then save the position. This would be at least once. In this case, there is a possibility the consumer process crashes after processing the messages, but before saving its position. In this case, when the new process takes over the first few messages it receives, we'll already have being processed. This corresponds to the at least one semantics in the case of consumer failures. In many cases, messages have a primary key, and so the updates are idempotent. Receiving the message twice just overrides a record with another copy of itself. So what about exactly what one semantics, i.e. the thing you actually want? When consuming from Kafka topic and producing to another topic, as in Kafka streams, we can leverage the new transactional producer capabilities in .11 version that were mentioned above. The consumer's position is stored as a message in a topic. So we can write the offset to Kafka in the same transaction as the output topics receiving the processed data. If the transaction is abort, the consumer position will revert to its old value, and the produced data on the output topics will not be visible to other consumers depending on their isolation level. In the default read uncommitted isolation level, all messages are visible to consumers even if they were part of an aborted transaction. But in read committed, the consumer will only return messages from transactions which are committed. When writing to an external system, the limitation is in the need to coordinate the consumer's position with what is actually stored as output. The classic way of achieving this would be to introduce the two-phase commit between the storage of the consumer position and the storage of the consumer output. But this can be handled more simply and generally by letting the consumer store its offset in the same place as the output. This is better because many of the output systems a consumer might want to write to will not support a two-phase commit. As an example of this, consider Kafka connector, which populates data in HDFS along with offset of the data it reads so that it is guaranteed that either data and offsets are both updated or neither is. We follow similar patterns for many other data systems which require these stronger semantics and for which the messages do not have primary key to allow for the duplication. So effectively, Kafka supports exactly once delivery in Kafka streams, and the transactional producer consumer can be used generally to provide exactly once delivery when transferring and processing data between Kafka topics. Exactly one delivery for other destination systems generally require cooperation with such systems, but Kafka provides the offset which makes implementing this feature feasible. Otherwise, Kafka guarantees at least one delivery by default and allows the user to implement at most once delivery by disabling the retries on the producer and committing offsets in the consumer prior to processing batch of messages. So basically what they said here about the exactly one semantics is that Kafka is using a combination of features like so to achieve exactly once. Exactly once. They use two things. One, idempotency, and two, they use like they have transactions. They use transaction, and with this they achieve this exactly once. So with idempotent producers, Kafka producers can be configured to be idempotent. This means that even if a message is sent multiple times due to network issues or retries, it will be treated as a single message because it's idempotent. For transactions, Kafka support basically the transactions. They allow the producers to send messages as part of a transaction. And this will ensure that either all messages in the transaction are processed or none at all. If there's, this is why they talked about the read committed, isolate, right? Read uncommitted. If there is a failure during the process, the transaction is rolled back. So by using these features in tandem, Kafka can ensure that messages are not duplicated and are delivered exactly once, even if in the presence of failures. 4.7 Replication. Kafka replicates the log for each topic partitions across a configurable number of servers. You can set this replication factor on a topic-by-topic basis. This allows automatic failover to these replicas when a server in the cluster fails, so messages remain available in the presence of failures. Other message systems provide some replication-related features, but in our totally biased opinion, this appears to be a tackled-on thinking, not heavily used and with a large downsides. Replicas are inactive. Throughput is heavily impacted. It requires fiddly manual configuration. Kafka is meant to be used with replication by default. In fact, we implemented unreplicated topics as replicated topics where the replication factor is 1. So even in cases you ask the topic to be unreplicated, it's replicated with the replication factor 1. The unit of replication is the topic partition. Under non-failure conditions, each partition in Kafka has a single leader and 0 or more followers. The total number of replicas, including the leader, constitute the replication factor. All writes go to the leader of the partitions, and reads can go to the leader or the followers of the partition. Classic write to the leader, read from the everyone. Typically, there are many more partitions than brokers, and the leaders are evenly distributed among brokers. The logs on the followers are identical to the leader's log, all have the same offsets and messages in the same order, though of course at any given time the leader may have a few as yet unreplicated messages at the end of its log. Followers consume messages from the leader just as a normal Kafka consumer would and apply them to their own log. Having the followers pull from the leader has the nice property of allowing the follower to naturally batch together log entries they're applying to their log. As with most distributed systems, automatically handling failures requires a precise definition of what it means for a node to be alive. In Kafka, a special node known as the controller is responsible for managing the registration of brokers in the cluster. Broker liveness has two conditions. 1. Broker must maintain an active session with the controller in order to receive regular metadata updates. 2. Broker acting as followers must replicate the writes from the leader and not fall too far behind. What is meant by an active session depends on the cluster configuration. For KRAF cluster, an active session is maintained by sending periodic heartbeats to the controller. If the controller fails to receive heartbeats before the time configured by the broker session timeout.ms, I think this starts to mean we won't need to read the configuration section. We already get here some configurations, some important. Expires, then the node is considered offline. For clustered using Zookeeper, liveness is determined indirectly to the existence of an ephemeral node, which is created by the broker on initialization of its Zookeeper session. If the broker loses its session after failing to send heartbeats to the Zookeeper before expiration of session timeout.ms, then the node gets deleted. The controller would then notice the node deletion to Zookeeper watch and mark the broker offline. We refer to nodes satisfying these two conditions as being in sync to avoid the vagueness of alive or failed. The leader keeps track of the set of in sync replicas, which is known as the ISR. In sync replicas. If either of these conditions fail to be satisfied, then the broker will be removed from the ISR. For example, if a follower dies, then the controller will notice the failure through the loss of its session and will remove the broker from the ISR. On the other hand, if the follower lags too far behind the leader but still has an active session, then the leader can also remove it from the ISR. The determination of lagging replicas is controlled to replica lag time max MS configuration. Replicas that cannot catch up to the end of the log on the leader within the max time set by the configuration are removed from the ISR. In distributed systems terminology, we only attempt to handle fail recover model of failures where node suddenly cease working and then later recover, perhaps without knowing that they have died. Kafka does not handle so-called Byzantine failures in which nodes produce arbitrary or malicious responses. So perhaps due to bugs or full play. So they do not handle the Byzantine failures, which is malformed failures. We can now more precisely define that a message is considered committed when all replicas on the ISR of that partition have applied it to their log. Only committed messages are ever given out to the consumer. This means that the consumer needs not worry about potentially seeing a message that could be lost if the leader fails. Producers, on the other hand, have the option of either waiting for the message to be committed or not, depending on the preference for trade-off between latency and durability. This preference is controlled by the AX settings that the producer uses. Note that topic have a setting for the minimum number of in-seq replicas that is checked when the producer requests acknowledgement that a message has been written to the full set of in-seq replicas. If a last string get acknowledgement is requested by the producer, then the message can be committed and consumed. Even if the number of in-seq replicas is lower than the minimum, it can be as low as just the leader. The guarantee that Kafka offers is that the committed messages will not be lost as long as there is at least one in-seq replica alive at all times. Kafka will remain available in the presence of node failures after a short failover period, but may not remain available in the presence of network partitions. Replicated logs, quorums, ISRs, and state machine. Oh my! And you know what? Oh my! We're going to pause here. This will be the part 1 of chapter 4. It looks interesting and it even becomes more interesting. Oh my! So the rest of it would be on part 2. And let's hope that there won't be part 3. I mean, it would be good to have part 3, but life is short.